Greeting of the day. I am Dr. Rasmita Jena, working as Assistant Professor in the Department of the Physics, Madanapalle Institute of Technology and Science, Andhra Pradesh. So today I will discuss about the topic Introduction to the Semiconductors. So first we'll discuss about the what is semiconducting materials, how the band is forming in a solids, that is nothing but the formation of the band, and based on the formation of the band we need to discuss about the what are the different classification of the solids based on the band theory only. And lastly we'll discuss what are the different type of the semiconducting material exist. So let's start with the introduction of the semiconducting materials. So as we know that a matter is nothing but the constituent of solids, liquids and the gas. Again, the solids are, as you know, it is nothing but the conductors, insulators, and the semiconductors. And the conductors is, we know that generally the metal materials is belongs to the conducting materials, and the insulator means these are nothing but the dielectric materials. The examples are we know as usual in the daily life: wood, glass, air. These are the insulating materials, and the semiconducting materials, which is today's days it is more important for the technologies application. So we'll more discuss about the semiconducting materials like germanium, silicon, gallium arsenide and many other materials that exist. And these semiconducting materials are exist in both the pure and the impure form in our nature. So in the pure form we can call it is intrinsic semiconductor, and in pure form of this semiconducting material we can call it is extrinsic semiconducting materials. So the pure form of the intrinsic semiconductor means no need to add any extra impurities to it. It is in the pure form. The examples like germanium and the silicon. These are the pure semiconducting materials. But the impure, or to form this extrinsic semiconductor, we need to add the extra impurities to that semiconducting materials so that we can improve its conductivity. So for that purpose, it is known as the extrinsic semiconductors. And also the extrinsic semiconductors are of the two types, P-type semiconductors and the N-type semiconductors. So in this today topic, we'll discuss more about these semiconductors, what is the pure and impure semiconducting materials and its type, the impure or extrinsic semiconductor, its type P-type and N-type, more details in the few slides. The first we'll discuss about this band theory of the solids. So as we know that how the solid is forming or how a crystal or a material is forming in the microscopic or in the atomic level. So it is nothing but the made up of the different atoms and the molecules. So these atoms is also having the electrons, protons, neutrons, everything is present inside the atoms. So here as first I have written that the isolated atoms are brought together to form a solid. Means we need to take closer the more atoms to form a solid or crystal. And the force of attraction and the repulsion between the atoms will find the balance at a proper interatomic spacing for a crystal. So to bring that atom more closer, there exists the attraction and the repulsion force between that atoms, right? So on that basis only the atoms are arranged inside a crystal or inside a solid materials. So here if I will take one example, silicon, which having the valency electrons n is equal to 4, 4 in number of electrons is present in the outer shell, which is nothing but the valency orbit or valence shell. So depending upon that valency electron, the interaction will be exist in between the other atoms which are present neighborhood of that silicon atoms. So on that basis, when one atom is present and the surrounded by this one single silicon atom, other silicon atoms are present, so it will be interact with their valency electrons only. it will also interact, it can also able to interact with the inner electrons which are present inside also. But due to the nuclear force is very much strong towards this nuclear or towards this inner electrons, so it cannot able to interact with the other silicon electrons. So that's why here more dominating thing is the valency electron interactions. The electrons which are present in the outermost cell, they will interact with each other and they will try to form a band, energy labels. Suppose I'll go to the next slide. So here in the band theory of the solids, in the lower diagram you can able to see, suppose I have taken a two atoms more closer to each other. So what will happen? Suppose the example I have taken a silicon atoms, two silicon atoms, which having the outermost 4 electron is present, right? So what will happen when these two valence electron of these two silicon atoms interact with each other? So there the energy level splitting will happen. So suppose initially if the single atom is present having the one energy level, so if the two atoms will be come closer to each other, so there will be the splitting of the energy level happen. So now the single energy level is splitted into the two energy levels. This is nothing but the discrete energy levels. So in the along the x-axis I have taken the r, which is nothing but the distance between the two atoms. That is nothing but the interatomic distance, and along the y-axis I have taken the electron energy. So when you bring the two atoms more closer to each other, means you are reducing the interatomic distance. So the electrons which are present outermost orbit of that two atoms, they will interact with each other and they will split that single energy level into the two energy level. Similar way, if I will bring the 6 silicon atoms more closer to each other, so similarly the single energy level will be splitted into the 6 energy levels. Similarly, in a solid, as you know that it is made up of the n number of atoms. So if the n number of the atoms come closer to each other, so the single energy level will be splitted into n number of the energy levels. So let's take an example of the silicon atom. So suppose in the top diagram you can able to see, this is nothing but the how the band is forming. We'll discuss more clearly here. Suppose you can able to see here the inner level and the inner cells, middle cells and the outer cells you can able to see, right? So the inner cell means, suppose we know that the silicon crystal is having 1s orbit, 2s orbit, 2p, 3s and the 3p cells are present here, there. So in the 1s orbit, if I will bring the n number of the silicon atoms more closer to each other, in the 1s orbit, 2n number of electron is present, right? Similarly, in the 2s orbit, 2n number of also electron is present. Similarly, 2p orbit, 6n number of electron is present. Similarly, in the 3p, 2n and in the 3p, 6n number of electrons is present. So the electrons or the orbits which are present in the inner cell, so when you bring the n number of the atoms more closer to each other, the inner cell splitting will not affected that much as compared to your outer cell, right? The interaction is there, the splitting of the energy level is there exist, but it is not that much of prominent as compared to the outer cell, right? The electrons which are present in the outer cell orbit, they will interact with the more prominently with the other electrons in the other silicon atoms as compared to the electrons in the inner cells, right? So what will happen if you will go to that outer cell? In the outer cell, so that is nothing but the your 3s and the 3p cell, right? In that cell, how many number of electrons is present? There 2n number of electron is present and the 6n number of electron is present. So in the outer cell is nothing but the your 3s and the 3p cell. In that cell, 2n number of the electrons is present. Also in the 3p cell 2n number of the electron is present. But in the 3p state, there is 2n state is present, and in the 3p 6n number of state is present. But when we bring the atoms, two silicon atoms more closer, so what will happen? These two cells, 3p and 3s cells, will be merged together at a certain distance, interatomic distances. So these two energy levels, these two cells will be merged at a single point, and now in that region 2n number of states is present, means total here now the 8n number of state is present, but 4n number of electrons is available in that merged region, right? So again, if I will reduce the interatomic distance between the two atoms further, so again the splitting of the energy level, the merge which is merged before, that energy levels, it will be start again splitting. So that is at that distance, the interatomic distance is nothing but is called the equilibrium interatomic distance. Means beyond that we cannot reduce the distance between the two atoms. That is the equilibrium interatomic distance. So what will happen at that point? The energy level which is merged before, it will be start splitting once again. And in the, you can able to see there will be the lower energy state is there and the upper energy state is there. In the lower energy state, now 4n state is available, and also as well as in the same in the upper 4n number of state is available. But we know that before in the merging region, we know that how many electron is present? 4n number of electron is present. But the electron first occupy the lower energy state or lower energy band. If there the extra electron will be exist, they can later go to the upper energy level. But in the lower energy level, 4n state is present and the 4n electron is also present. So it will be occupy the lower energy band. So in the upper energy band will be completely empty. So there exists a gap between the upper energy level and the lower energy level. So this is nothing but your band gap or energy gap between this upper and the lower energy level. So now here the band gap or this energy gap is come out from this interaction between the different silicon atoms in a solid. So like this way, in our solid or in the silicon crystal, many silicon atoms are present. So that like this way, the many bands are forming, so that the band gap is also coming out, right? So this is nothing but the how the band is forming in a solid. So let's discuss in the next slide. Based on the band theory, so the solids are classified into the three. We know that. We will discuss that more. But before that, we will discuss what do you mean by this valence band, conduction band, forbidden band or energy gap. So as you can see in that figure, so we have taken the interatomic distance along the x-axis and the electron energy along the y-axis. So the distance or the gap between the topmost energy level, which is nothing but your conduction band, and the lowest energy level, which is nothing but your valence band, that gap we are calling band gap, right? So first we know that what do you mean by the valence band. So as the valence band is nothing but the allowed or permitted energy levels for the electrons which are completely or the partially filled. Means suppose at the room temperature, if a silicon crystal is in the room temperature, right? We are not applying the any extra temperature, any extra heat to that semiconducting materials. So what will happen? The valence band will be completely filled by the electrons. Means the electrons which are covalently bonded with each other and present in that valence band. So all the electrons are present in the valence band. There is no extra electron present in the conduction band at normal temperature or room temperature, right? So in the conduction band means the allowed energy level for the electrons at the conduction are free which are partially filled or empty. So when the conduction band or the conduction electron will come out, so when you increase the temperature of that system or that crystal or the solid, so what will happen? the electrons which are present in the valency band with the covalent bonding with each other. So with a certain increase of the temperature, the electron will acquire or gain the energy and they will break that covalent bond. And now they are excited and jump to the conduction band. So now the few electrons is available in that conduction band when you increase the temperature of that system. So that electron is nothing but your conduction electron also, or free electrons. These electrons only responsible for carrying the charge, current, field one place to the other in our conducting materials. Similarly, what do you mean by that forbidden gap, energy gap and the band gap? Right? So here, as we know that this band gap is nothing but the gap between the valency band and the conduction band. Right? Means if I'll tell more details here, so the gap is nothing but the distance between that topmost energy level of the valence band EV and the lowest energy level in the conduction band EC. That gap is actually called the band gap or forbidden gap or energy gap. Why the name is like this way, forbidden band? Because in that gap or in that region there is no energy level exist. For that, electron can occupy that energy levels. So that's why that name is forbidden band or energy gap or band gap. So based on this forbidden band, energy gap and the band gap, the solids are classified into the different types. So the solids are classified into the three types based on only that band gap. So first is your conductor, semiconductor, insulator. So in the conductors, what will happen in that conducting materials or the conductors are those substances which easily allows the passage of the electric current through them, right? So you can able to see the diagram, corresponding diagram in the left side figure also. So in the conductor case, what will happen, that valency band and the conduction band overlap with each other. There is no gap exist between the valency band and the conduction band. So when you increase the temperature of that system, so easily the electrons which are present in that valency band, they can break their covalent bond and easily go to the conduction band. So that more number of the free electrons available in the conduction band. So there is no gap exist in case of the conductor, so that there will be no extra energy required to excite the electrons to the conduction band. So here in terms of the energy band, the valence band and the covalent band is overlap with each other in this conductor. And here the resistivity of the conductors are in the order of the 10 to the power minus 8 ohm into meter. Here the resistivity in the order of the 10 to the power minus 8, because here the more number of the free electrons are available, right? So what are the examples of the conducting materials? Like aluminium is there, copper, iron, many more materials are there. So similarly, the next is your semiconducting materials. So the semiconducting materials are nothing but the material whose electrical conductivity lies between the conductors and the insulators. So you can able to see the second diagram, middle one, in which you can able to see there is the exist a gap between the valency band and the conduction band. So here the valency band, that band gap is nothing but 1 electron volt, right? So if you increase the temperature of that system, the electron will be jump to the conduction band, but it will require that band gap amount of energy to excite the electron or to transport the electron to the conduction band. That energy is directly proportional to your band gap. That is nothing but your here 1 electron volt. Similarly, based on the different elements, different materials, that band gap energy will be vary in case of the semiconducting materials. So here, as compared to the conductor, here in this semiconducting material there exists a band gap. But in case of the conductor, there is the overlapping of the conduction band and the valence band. There no exist of this band gap. But in case of the semiconductor, it is little developed. That gap is developed, and based on that materials and the elements, that value will be vary, the band gap value. So if I will take the example of the silicon, it is having the 1.1 electron volt of that band gap energy. Similarly, germanium 0.7 electron volt, gallium arsenide, the value is 1.43 electron volt. Similarly, for other different semiconducting materials, the band gap will be vary. So here, by the thermal excitation, the electron is moving from the valence band to the conduction band. But at the normal temperature or the room temperature, this semiconducting material will behaves like an insulator. Why the semiconducting material behaves like an insulator at the room temperature? Because there is no free electron available in the conduction band. At the room temperature, all the electrons are present in the valence band and it is covalently bonded with each other. That's why the semiconducting material behaves like an insulator at the normal temperature or the room temperature. But when you increase the temperature of the system, the electrons break their bond, covalent bond, and jump to the conduction band. So, with the increase in the temperature, the semiconducting material having the more number of the electrons, free electrons in their conduction band to carry the charge or to transport the electricity or current. So what are these examples of that semiconducting materials? As you know that the well-known examples are germanium, silicon, gallium arsenide, aluminum arsenide, and many other materials exist. So similarly, the last is insulator. So the insulator is nothing but the substance which does not allow the passage of the electric current through them. Why the insulator does not allow the electric current through them? As you know that in the conducting materials, the free electron is available. In the semiconducting materials, when you increase the or when you provide the some amount of the energy, then only the free electrons is available. But in case of the insulator, the electrons, the atoms are present. Suppose I will take the example of the wood or glass, right? The atoms are present there, but there is non-availability of that free electrons. The electrons is present, but the electrons which are present inside the atoms, it is tightly bound or closely bound with each other. So there is non-availability of that free electrons. So due to that only, it cannot able to passes the electric current or any heat through it. So in terms of the energy band, in this case, in the insulator case, the band gap is very high as compared to the semiconducting materials. So the band gap range is 6 electron volt to 15 electron volt, and it can vary from the one insulating material to the other insulating materials. So the examples are the wood, glass, plastic. As you know that these are the common examples of the insulating materials. And here the resistivity of that insulating material is very high. It is nothing but the order of the 10 to the power 7 ohm into meter. But in the conductor case, the resistivity is very low because the more free electrons is available. So based on this band gap, just before we discuss the semiconductors and the insulators. In case of these conducting materials, the band gap is not exist, means it is approximately 0. In case of the semiconductors, the value will be started increasing the band gap value 1 electron volt, and it can vary more than 1 electron volt also for the based on the different semiconducting materials. And the insulator, which is having the high energy gap or band gap, the range is 6 to 15 electron volt. So now we'll discuss how the charge carriers or how the transport of the charge carriers is exist or impossible in case of the semiconducting materials, right? So in the semiconducting materials, the valency band is completely filled by the electrons and the conduction band is completely empty at room temperature, right? So when you apply some external heat or any magnet field, whether it will be the electric field, magnetic field, anything you need to apply, so the electron will be gain the energy and break their bond, covalent bond, and jump to the conduction band. Now the empty space is available in the valency band, but at the same time the free electrons is available in the conduction band, right? So based on the free electron, how many, if the more number of the free electron is present, the semiconductors will behaves like a, means carry the more current or allows the more current to it, right? So based on that the electron hole pair is created at the same time. So you can able to see from that diagram, when I increase the temperature T greater than 0 Kelvin, what will happen? The electron break their bond, covalent bond, jumping to the conduction band, right? At the same time, the absence of the electron is nothing but your hole, right? Positive charge. At the same time, the electron is present in the conduction band. So this is nothing but the generation of the electron hole pairs in a semiconducting material when you increase the temperature from the 0 Kelvin to or above the 0 Kelvin. Similarly, the recombination is also happen in the semiconducting materials. So first, when you increase the temperature T greater than 0 Kelvin, the electron hole pair is generated, right? So again, up to the certain time, the electron can exist in the conduction band. There is the lifetime of the electron is also there. So that time is nothing but the lifetime of the electron, and the duration is 10 to the power minus 8 second. Means the electron can exist up to 10 to the power minus 8 second in the conduction band, and it will be again coming back to its valency band by releasing or by emitting the energy. So that process is nothing but called the recombination. So the recombination is nothing but the process of combining the conduction electron with the valency hole is known as the recombination. So in the left side diagram, here the recombinations, first in the first arrow mark you can able to see the electron is left the valency band and jump to the conduction band by acquiring or by gaining the energy. But in the valency band, it will be stay up to the 10 to the power minus 8 second and coming back to this own valency band. At that time, the electron will release that energy and coming down its valency band. So that whole process is nothing but, first it is called the electron hole pair, and that electron will be stay in 10 to the power minus 8 second in the conduction band. It is called the lifetime of that electron, and that electron again coming back to its valency band, it is called the recombination process. So here in this semiconducting materials, this empty state is known as holes. We know that it is available in the valency band and having the positive charge, right? And the electrons present in the conduction band. So the electron in the conduction band move to the opposite to an electric field, while the hole in the valency band move in the direction of the electric field. So when you apply the electric field or current to a semiconducting material, what will happen? So the electron gain the energy jumping to the conduction band, the hole will be present in the valency band. To fill this hole, the nearest free electron or nearest electron will be jumped to that hole. Similarly, another hole will be generated in the second place. Similarly, the other electron or nearby electron will jump to that hole. So, like this way, the transforming or the moving of the electrons or the flow of the electrons or the current will happen in a semiconducting material. But it is opposite to that direction of the electric field. The flow of electron is opposite to the flow of the electric field. So similarly, what are the types of the semiconducting materials? So the semiconducting materials are of the two types. First is your intrinsic semiconductor, which is nothing but your purest form of the semiconducting materials. So the intrinsic semiconductor is nothing but a perfect semiconducting crystal with no impurities. A lattice defect is called as the intrinsic semiconductors. Like I have given the examples germanium, silicon, these are the purest form of the semiconducting material. At T is equal to 0 Kelvin, no charge carriers available because the conduction band is empty and the valency band is filled by the electrons. Right? Just before we discuss, at the 0 Kelvin, there is no extra electron is available in the conduction band. So when we increase the temperature, so the electron hole pair EHP, the electron hole pair is generated, and these are the only charge carriers in the semiconducting materials. So which both the electron and the holes carry the current in the semiconducting materials. But in case of the conductor, only the electrons are the charge carriers. So here the example I have taken in a silicon crystal, if one of the covalent bond is broken by the thermal energy, then the free electron move to the conduction band and the broken bond hole is left in the valence band. And in the diagram, in the left side diagram, you can able to see, so to fill this hole, the electron is, the nearest electron is coming to that hole. Like this way, the transfer of the electron or the movement of the electron is happen inside that semiconducting material. So in the intrinsic semiconductors or in the pure semiconductors, the energy required to break the bond is the, as you know that this is nothing but the energy gap or the band gap. As the electron and holes are created in the pairs, nothing but the electron hole pairs, the conduction band electron concentration is equal to the concentration of the holes in the valency band. So in case of the intrinsic semiconductor, how many number of free electron available in the conduction band? Same number of the holes is also present in the valency band. So if I will take the concentration of the electron notation is N and the concentration of the hole notation is P, in case of the intrinsic semiconductor, that N is equal to P. So that is nothing but the Ni, the intrinsic carrier concentration. So the next is recombination takes place when an electron in the conduction band makes a transition direct or indirect to an empty state. The holes in the valency band, thus the annihilating the pair. So as we discussed, the electron cannot stay lifetime in that valency band. It will be come back to its original band, valency band. So at that time, the annihilation is occurs or the energy loss will be occur by that electrons. So similarly, the next is exchanging semiconductor or the doped semiconductor, or it is nothing but the impure semiconductor. Why it is called the impure semiconductors? Then what is the necessary of that exchanging semiconductors? In our nature, these semiconducting materials, the pure semiconducting materials is available. Germanium, silicon, everything is available. Why we are going for that exchanging semiconductors? What is the conductivity of that semiconducting materials? It is not that much of sufficient from the application point of view. We need to enhance or increase that conductivity of that semiconducting material. We need to add the extra impurities. That is nothing but your exchanging semiconductor or the doped semiconductor. So the main aim is to enhance its thermal or the conductivity properties. So the process of the adding of that impurities is called as doping, right? So when a crystal is doped such that the equilibrium carrier concentration N0 and the P0 are different from the intrinsic carrier concentration Ni of the material is said to be extrinsic. That means in case of the intrinsic semiconductor, how many number of free electron is available, same number of the holes is available in the valency band. But in the extrinsic semiconductor case, that concentration of the electron and holes is not equal because we are adding the extra impurities to it. So that's why the concentration of the electron is not equal to the concentration of the holes in case of the extrinsic semiconductor. So in these extrinsic semiconductors, so what is the main aim or main theme to prepare this extrinsic semiconductor in artificially? To increase their electrical conductivity or increase their thermal properties of that materials, of that semiconducting materials, right? So these extrinsic semiconductors are two types based on the doping element. So what are these types? First is your N type and second one is your P type semiconducting material. So in this diagram you can able to see this N type semiconductors is formed when you add the pentavalent impurities to it. So what do you mean by pentavalent impurities? Suppose you have taken a silicon or the germanium crystal or solid which is having the 4 electron in its outermost shell. But if you are adding the pentavalent impurities, suppose the example is I have taken here Pb, or you can take the any other elements, pentavalent elements. So in the pentavalent means that element is having 5 valence electron in its outermost orbit. So as you can able to see, so in the lower diagram you can able to see, so here if you add the pentavalent impurities, so the 4 electrons, suppose the example I have taken the Pb, in the first case I have taken the example Pb case. So the 4 electron will be make the covalent bond with the 4 silicon atoms which are present neighborhood of that Pb, but the 1 electron is still left in the Pb orbit, in the outermost orbit, which is not able to make the covalent bond with other silicon atoms because the 4 are already make the covalent bond with the 4 electrons of the Pb. So that electrons is nothing but your donor impurities. And where this electron will occupy? So this electron will make the another energy level. It is called the donor energy level. So similarly, suppose if you are adding the 1 Pb atom, then you are getting the 1 free electrons. Similarly, if you add the 1000 number of the electrons, 1000 number of the Pb atoms, so 1000 number of the free electrons is available. So where this free electron will occupy, or this donor impurity will occupy? So they will make the another energy level exactly below that conduction band. So in the lower diagram you can able to see clearly. So the atoms, the free electrons which are not able to bond the covalent bond with the other silicon atoms, they can occupy that ED energy level, donor energy level. So when you increase the temperature of that system, that electron will easily transfer or jump to that conduction band and they will make as free electrons and they will participate in the conduction process in case of the extrinsic semiconducting materials. So in case of the N-type semiconducting materials, we are getting the more number of or excess of the electrons. This is nothing but your donor impurities or donor electrons it is, right? So here in the N-type semiconductor, what are the majority charge carriers? Majority charge carrier is nothing but your electrons because we are having the excess of electrons. But what are the minority of the charge carriers? The minority of the charge carrier are the holes here. Similarly, in case of the p-type extrinsic semiconductor, so what will happen in case of the p-type? So the p-type semiconducting materials is able to form by adding the trivalent impurities to the silicon crystal or silicon solid. So example is, suppose I have taken the aluminium. So the aluminium is nothing but the trivalent impurities. The trivalent means it is having the 3 outermost electron in its outer orbit or the valence cell. So these 3 electron will make the covalent bond with the 3 neighborhood silicon atoms. But the one backend will be created or hole will be created. As you can see in the lower diagram, it is clearly visible. So the aluminium atom is making the covalent bond. The 3 outermost electrons is making the 3 covalent bond with the 3 silicon atoms, but the one hole is present because due to the unavailability of the electrons in the aluminium. So here this hole is created. This is nothing but your acceptor holes, right? So if you are adding the one aluminium atom or one trivalent impurities, you will get the one hole. Similarly, if you add the n number of the aluminium, n number of the n trivalent impurities, so you will get the n number of the holes. So where these holes will be lie? So they will make the another energy level, nothing but your acceptor energy level EA. In the second diagram you can able to see. So in that EA energy level, all the electrons will be occupied there. So when you increase the temperature of that system, so the electron which are present in the valency band, they can easily transport to the acceptor energy level, right? So similarly, it can easily jump to the conduction band. So like this way, in the p-type semiconductor, the conduction process will happen. So what is the definition of that n-type and how it is created? So the n-type, it is created by doping with the element that have more valency electrons than the semiconducting materials. Like if you are taking the silicon or germanium, which is the trivalent, and if you are adding the more valency electrons means the pentavalent impurities, then you can form the n-type extrinsic semiconductors. And what are the majority and the minority charge carrier? The majority charge carrier are the electrons because more number of the free electrons is available as compared to the holes. So the holes are the minority of the charge carriers. But in case of the p-type, it is created by the doping with the element that have the less valence electron than that semiconducting materials. Suppose you have the silicon germanium tetravalent crystal. So if you add the less valence electron means trivalent impurities to it, so you can able to form that p-type extrinsic semiconductor. So in the p-type extrinsic semiconductors, the holes, more number of the holes is available. So the majority of the charge carrier are the holes and the minority of the charge carrier are the electrons in the p-type extrinsic semiconductors. So from this discussion of this introduction to semiconductor, so we'll discuss about the what is semiconducting materials, how the band is forming inside the semiconducting materials, and based on that band gap, the solids are classified into the 3 types: conductor, semiconductor, and the insulators. And also, the semiconductor is on 2 types based on the charge carriers, intrinsic and the extrinsic. And to enhance the conductivity properties of the semiconducting materials, we have added the impurities, which is nothing but your extrinsic. Again, the extrinsic semiconductors are of the 2 types, that is n-type and the p-type, based on the pentavalent or the trivalent impurities adding. So based on the impurities, the majority and the minority charge carrier will be exist. So this is all about the introduction to the semiconductors. Thank you.